In this lesson, we're going in the opposite direction as the last lesson. In the last lesson, we knew that we had a parallelogram, and then we knew that the figure had properties. In this lesson, we're talking about what properties a quadrilateral can have that would then guarantee that the quadrilateral is a parallelogram. Well, we already know the definition of a parallelogram, that it has two pairs of opposite parallel sides. So if we know that a figure has two pairs of opposite parallel sides and it's a quadrilateral, then we can use the definition to say that that quadrilateral is a parallelogram. But we can also use a lot of the converses of yesterday's theorems to also prove that something is a parallelogram. For example, if both pairs of opposite sides of a quadrilateral are congruent, then I know that the quadrilateral will be a parallelogram. So if I have a figure where I know this is congruent to this, and I know that those opposite sides are congruent, that allows me to conclude that this is a parallelogram. So here we have the proof of that theorem. So very much like the last one, I start by drawing a segment because through any 2 points there's exactly one line. So that's an auxiliary segment. I know that that segment's going to be congruent to itself because of the reflexive property of congruence. Segment AB congruent to CD, AD congruent to CB, that was given to me. So this proof is already a little bit different than other proofs in that we didn't start with the given, but you know you're going to use it. And look at what we have. I have 1, 2, 3 pairs of congruent sides. So these triangles are congruent by side, side, side. Remember that anytime you're going further than saying that two triangles are congruent, and saying that parts of those triangles are congruent, you're using CPCTC. So let's look at these angles that they said are congruent. Angle ABD and CDB, and angle ADB and CBD. Well, those are the angles that we were dealing with in the proofs from yesterday's video. It's the same kind of angles, but since we're using the angles to say that the lines are parallel, you want to be really careful and make sure you're saying that this is the converse of alternate interior angles theorem. And then once I know that both pairs of opposite sides are parallel, then this is a parallelogram by the definition of parallelogram. Another theorem we have is that if one pair of opposite sides are both parallel and congruent, then the quadrilateral is a parallelogram. So again, let me illustrate that. If I have one pair of opposite sides that's congruent and parallel, so you really, if you haven't figured out what the markings on a diagram mean, you need to figure it out now. Hash marks indicate congruent, arrowheads indicate parallel. So in this example, I have that a quadrilateral has two sides that are 3 centimeters long and two sides that are 5 centimeters long. And a student states that the quadrilateral must be a parallelogram. Do you agree? Well, some of you may have the gut instinct to say, yes, if I have two pairs of congruent sides, then that's enough. However, it only said that there are two sides. It didn't say that they were opposite congruent sides. This could be a kite, which is a figure that we'll talk about later on in this module. But based on the description, this could be what we're looking at, and that is not a parallelogram. Okay, so no, it could be a kite. Furthermore, congruent sides have to be opposite. To be a parallelogram. And here we're proving another theorem that if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Here we are proving that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So we are given that angle A is congruent to angle C and angle B is congruent to angle D. And again in this proof, we're not starting with that which we were given, we're starting with some additional information that is kind of helpful to us. So we know that the measure of angle A plus measure of angle B plus measure of angle C plus measure of angle D equals 360 by the polygon angle sum theorem. And from the given, if angle A is congruent to angle C, then the measure of angle A equals the measure of angle C. Similarly, the measure of angle B will equal the measure of angle D. So by substitution, I have the equation that you see here. I can combine my like terms and get that 2 times the measure of angle A plus 2 times the measure of angle D equals 360. So that means that measure of angle A plus measure of angle D equals 180. So angles A and D are supplementary, and that makes line AB parallel to line DC. Again, be very careful. This is the converse of the same side interior postulate. And since a similar argument would show that AD is parallel to BC, once again, ABCD is a parallelogram by the definition of parallelogram. Another property that we knew about parallelograms in yesterday's video is that the diagonals bisect each other. So here, we're proving that if the diagonals of a quadrilateral bisect each other, then that quadrilateral is a parallelogram. So I'm starting with the given this time. That's convenient. And then I'm saying angle AEB and CED are congruent, as well as AED and CEB. Those are vertical angles. So what I'm using here is the vertical angle theorem. So look at what we have. We have these congruent sides that they gave us, all these congruent angles. So that means we've got a bunch of congruent triangles in here. So I can say that triangle ABE is congruent to triangle CDE, and that triangle BCE is congruent to triangle DAE, and both of these pairs of triangles are congruent by side angle side. And then once again, after I've said that 2 triangles are congruent, what property am I using? I'm using CPC-TC. Let's look at how we're using CPC-TC. We're using it to say that AB is congruent to CD, BC is congruent to AD. We've already proven that if 2 pairs of opposite sides are congruent, that makes it a parallelogram. So that's the theorem that we're using. If opposite sides are congruent, then parallelogram.